Welcome back to the Deep Dive. Today we're diving headfirst into a topic that, well, it really underpins almost every meaningful data insight: data wrangling. We're drawing our insights from Professor Davi Moreira's MGMT 17300 Data Mining Lab data wrangling sources, which lay out a clear, really actionable blueprint for transforming raw, often chaotic data.
Which it usually is.
Exactly. Into something clean, structured, and ready for some powerful analysis. Our goal for you today is a comprehensive, nuanced understanding of this absolutely essential skill, maybe peppered with some truly illuminating insights.
It's such a foundational topic. I mean, anyone who has ever tried to extract meaning from real-world data knows it rarely arrives in a pristine package.
Right.
Understanding these techniques isn't just about cleaning. It's about building a robust, trustworthy foundation for all the subsequent analysis and, well, ultimately for making more informed decisions.
So let's set the scene a bit. You just got your hands on a new data set. Maybe it's from a web scrape, maybe a legacy database, or just a simple CSV export.
Yep, the usual suspect.
And chances are it's not perfectly organized. It's got missing values, inconsistent entries, maybe even some structural oddities. It's, in a word, messy.
That's almost the universal truth of data science, isn't it? And there's a famous quote from Hadley Wickham, who's really a pivotal figure in this field,
Oh, yeah?
that perfectly encapsulates this challenge. Tidy data sets are all alike. Every messy data set is messy in its own way. I like that. It highlights the sheer diversity of messiness out there, but it also hints at a powerful universal solution, this concept of tidy data.
That quote really resonates. If every messy data set is unique in its chaos, how can one single conceptual framework, tidy data, provide a universal solution? What actually defines this, ideal state?
That's an excellent question, because tidy isn't just about being neat. It's a very specific logical structure, and it profoundly impacts how easily you can analyze and visualize data.
Okay.
A data set is considered tidy if, well, three conditions are met. 1, each variable forms a column.
Right.
2, each observation forms a row. And 3, each type of observational unit forms its own table.
Ah, I see. Like a grammar for data.
Exactly. Think of it as standardizing your data's grammar. When data follows these 3 rules, all the powerful analytical tools and functions can just work seamlessly.
Makes sense.
And the tools we'll be discussing today are part of the Tidyverse. It's a carefully curated collection of R packages, all specifically designed with these tidy principles in mind.
Right. The Tidyverse. It's huge in R now.
It really is. It's rapidly become the de facto standard for data analysis in R, precisely because it offers this consistent, intuitive, and frankly, highly efficient framework.
I appreciate that distinction. It's a standardized grammar, not just neatness. That's a crucial aha moment right there.
Yeah.
Okay, so let's unpack this concept of data wrangling. It definitely conjures up images of, taming something unruly.
Yeah, like wrangling code or wrangling cats.
Oh, yeah, but for numbers. When we talk about taming data, what are the most common challenges or, wild beasts we typically need to tackle in that initial raw state?
That taming metaphor is actually spot on. Data wrangling, or you might hear data cleaning or data munging.
Right, different names.
It's the entire iterative process of transforming that raw, often chaotic data into a structured format that's genuinely ready for rigorous analysis. The wild beasts often include, well, missing values, malformed values.
Like text where numbers should be.
Exactly. Or inconsistencies like, New York, NY, NYC, all meaning the same thing.
Oh, yeah, that stuff.
And inconvenient table formats like wide data when you need long data or vice versa. And sometimes just too much information or not enough, or it's just organized poorly. It's about more than just finding errors. It's really about preparing the data to tell a coherent story.
So going beyond just making data readable, what's the really profound impact of meticulously cleaning and structuring it? Why is this foundational step so often maybe underestimated in its power to transform an entire project?
This raises an absolutely critical question. The importance of data wrangling, well, it just can't be overstated. It really boils down to 3 core reasons, and each has these cascading effects.
Okay.
First, improved data quality. Simply put, unreliable analyses just cannot happen without clean, accurate, consistent data. It's the bedrock.
Right. Garbage in, garbage out.
Precisely. Imagine trying to predict flight delays with depth delay entries that are sometimes in minutes, sometimes hours, or just missing. Your model would be predicting nonsense. Clean data directly translates to reliable insights.
Makes sense.
Second, efficiency in analysis. Data prepared in a structured, tidy format significantly reduces the time you spend debugging errors later on.
Oh, I bet.
Instead of wrestling with data inconsistencies during the analysis phase, you can focus your mental energy on the actual insights, the model building, the interpretation. It accelerates your entire workflow dramatically.
Freeing up brain space.
Absolutely. And third, better decision making. This is the ultimate payoff, right? High quality, well-structured data directly leads to more meaningful interpretations, stronger conclusions, and ultimately more actionable insights. When business decisions are based on data that has been meticulously wrangled, the confidence in those decisions and their likelihood of success, it just increases exponentially. It's about trusting your numbers.
That's a really powerful argument for investing that time up front. Okay, to make this more tangible, our source material wisely advises adopting a project-based workflow. Apparently, this optimizes collaboration and sharing.
Yeah, it's good practice, keeping things organized.
And for our deep dive today, we're going to illustrate these concepts using a fantastic R package called Nike Flights 13.
Ah, yes, Nike Flights 13. It's a great one. It's a real treasure trove of data, providing several interconnected data sets about flights departing from New York City in 2013. The star of our show will probably be the flight's dataset itself. It contains info on all U.S. domestic flights departing the main NYC airports, JFK, LaGuardia, and Newark, throughout that year.
And inside this flight's data set, we've got some really useful variables, things like year, month, day for the departure date,
Standard date stuff.
dip delay and R delay for departure and arrival delays, and minutes,
Crucial for analysis.
carrier for the airline code, and origin and for the origin and destination airports. These are the kinds of variables you see all the time, right?
Absolutely. Very typical.
And we'll be using them to demonstrate the sheer power and flexibility of the Tidyverse. What I find truly compelling about the Tidyverse is it's very intuitive grammar for manipulating data. It feels like having a specialized vocabulary where each verb directly describes an action you want to take. It streamlines these complex processes into almost conversational steps.
That's precisely the design philosophy behind it. And what's really innovative is how these verbs are combined using the pipe operator, %, or the newer native R version.
Ah, the pipe, yes.
Think of it like a seamless conveyor belt for your data. You put your raw data on one end, and each verb along the line performs its specific task, passing the refined result directly onto the next step.
Okay.
This transforms what could be really complex nested operations like, remember some squirt, factorial, X.
Oh, yeah, hard to read.
Into a clear, linear workflow. X% factorial, %4% factorial. It reads almost like a sentence describing the data's journey.
Right.
It vastly improves code readability and makes your analysis far easier to follow, to debug, and importantly, to share.
That conveyor belt analogy really brings it to life. It makes these complex data pipelines feel much more approachable. Okay, let's start with our first set of powerful verbs, select and rename. Picking and labeling your columns.
Okay.
For anyone who's wrestled with SQL select statements or, Python's column indexing, Tidyverse's select offers a remarkably fluid and expressive approach. It feels like it's not just about picking columns, it's making column management more dynamic.
Absolutely. Select isn't just a basic column picker. It lets you choose columns by name, sure, but also by these clever patterns.
Like what?
For instance, flights %select, year, month, day, dep delay, R delay gets your core date and delay info. Simple enough. But you can also do select tilnum natch per time hour to drop columns you don't need, which is incredibly useful for those really wide data sets.
Oh, that is useful, the negative selection.
Yeah. Or if you have a naming convention, you can use things like starts with R or contains time to dynamically select columns based on patterns in their names.
Wow, okay.
You can even reorder columns easily, like select carrier, flight, everything. This puts carrier and flight right up front.
Indeed.
And rename is just as crucial for clarity. Changing carrier to the more descriptive airline is as simple as flights %rename, airline carrier.
Right. New name, old name.
Exactly. I remember once spending an entire afternoon debugging a dashboard because a data source silently changed customer to custom. A simple rename right at the start of the script could have saved us that headache. It protects you from upstream changes sometimes.
That's a perfect example of why naming conventions and that flexibility are so important. Yeah. Okay, so beyond just selecting, sometimes the real power comes from transforming existing data into new insights. This brings us to mutate and transmute, creating new insights. This feels like the heart of feature engineering, doesn't it?
It absolutely is. Mutate is arguably one of the most powerful verbs in the whole tidyverse. What's really profound isn't just adding a new column, but the ability to create these derived variables that unlock entirely new perspectives. And you do it without altering your original data inputs. Imagine you want to calculate the total delay for each flight. Simple. Flights percent mutate. Total delay plus depth delay, boom, new column.
Nice.
You can even layer multiple mutations, like create a delay category based on that total delay right in the same pipeline step. And mutate keeps all your original columns alongside the new ones, which is usually what you want. If you're building a predictive model, mutate is where you'd engineer features like, say, speed, distance airtime, or maybe a stress index combining various factors.
Right, combining things.
Layering complex transformations directly into your workflow, it's incredibly powerful.
And transmute is its more minimalist sibling.
Precisely. Transmute does the same calculations, but, and this is key, it only keeps the newly created variables. It drops all the originals.
Oh, okay. When would you use that?
It's perfect when you're performing an intermediate calculation and you only need the result for the next step in the pipe. It helps create a focused, temporary data set of just your engineered features. It's about efficiency and keeping your working data lean when you don't need the old stuff anymore.
Got it. Okay, categorization is such a cornerstone of analysis, but complex conditional logic, nested if-else's, can quickly make code unreadable.
Tell me about it.
So, moving on to case when. Categorizing and retoding. How does this verb offer a far more structured and readable way to build those complex multi-condition rules, especially when you're moving beyond a simple Eiffel?
Oh, case when is an absolute lifesaver for conditional logic. It offers such a clean, step-by-step approach that dramatically improves clarity compared to nested if-else statements.
That's how it works.
Instead of trying to parse tangled conditions, case when lets you define conditions on the left and their corresponding outcomes on the right using this tilde. It's very readable.
Can you give an example?
Sure. To categorize arrival delays, you might do flights percent mutate, delay status, case one, R delay 0 and R delay equals 60. Short delay, R delay 60. Long delay, true unknown.
Ah, okay. Condition, tilde, result.
Exactly. And notice the true unknown at the end.
Yeah, what's that for?
That's a crucial catch-all. It handles any rows that didn't meet the previous conditions, like maybe R delay was missing, NA. This ensures every single row gets a classification and no data is accidentally dropped or left unassigned.
That's really smart. Prevents errors.
It's incredibly robust for complex recoding tasks, like assigning risk levels or customer segments based on multiple factors, much cleaner than deep if-else trees.
That's incredibly helpful for preventing those unforeseen edge cases. Okay, so once we've got our data shaped and maybe categorized, we often need to drill down, right?
Okay.
To isolate specific observations that meet certain criteria. That seems exactly where filter, focusing on specifics, comes in.
Filter is essentially your magnifying glass for rows. It allows you to select rows based on logical conditions, narrowing your data set down to exactly what you need for a particular analysis.
Like just flights from January.
Yep. Simple as flights percent filter, par of Denton 1, or maybe you want to look at United Airlines flights only in January.
How would you combine those?
You use logical operators. Filter and filtermon, and carriers is EA. The N is A and D. You also have for OR and for not.
Okay.
These give you immense power to create highly specific subsets. You can even filter for missing values using is.na depth delay, or more commonly, filter them out with m.na depth delay.
Right, handling those NAs.
It's foundational for any targeted analysis. It lets you quickly zero in on patterns within specific segments of your data before you do anything else.
Makes sense. And once we've filtered, arranging our data for better readability or maybe to spot trends immediately becomes important. That seems where arrange, getting things in order, is vital.
Exactly. Arrange does one simple but crucial thing. It sorts your rows based on the values in one or more columns.
So finding the shortest delays.
Yep. Flights percent arrange, depth delay, would sort by departure delay in ascending order, smallest first.
Yeah, the longest.
You just wrap the column name in desk. So arrange would show you the flights with the largest arrival delays right at the top.
Desk for descending. Got it.
You can also sort by multiple columns, like arrange carrier depth delay would sort alphabetically by carrier first, and then by departure delay within each carrier group.
Okay. Useful for comparisons.
For sure. This seemingly simple operation is often crucial just for visual inspection or for preparing data for presentations or even for certain analytical algorithms that expect sorted data.
Right. Okay, so once we've maybe filtered and ordered our data, the next natural step is often to start aggregating, looking for those broader patterns, moving from individual observations to trends. This is where summarize and groupie. Getting the big picture must really shine.
Oh, absolutely. This combination is where a huge amount of analytical power lies in dplyr. Summarize on its own computes summary statistics for the whole data set. Think mean, sum, median, count.
Okay, like one number for the whole table.
Right. But it's when you pair it with groupie that it truly transforms your analysis. Groupie essentially splits your data frame into separate groups based on the values in one or more columns.
Like grouping by airline.
Exactly. And then summarize performs its calculations within each of those individual groups.
So instead of just one single average delay for all flights, you could get an average delay for each airline separately.
Precisely. That's the magic. For example, to find the mean departure delay for each carrier. Flights % group B carrier % summarize me end up delay. Nan up delay nan.rm equals 2u.
Okay, group B carrier, then summarize. And what's nan.a.rm equals 2u?
That's critical. It tells the mean function, and many others, to remove any NA or missing values before calculating the mean. If you don't include it, and there's even one NA in a group, the result for that group will often be NA.
Got it. So always remember nanny.rm equals true for calculations like mean or sum.
Generally, yes, unless you specifically want to know if NAs are present. Other incredibly useful summary functions here are sum, median, SD for standard deviation, N, which simply counts the number of rows in each group, and indistinct, which counts the number of unique values within a group. This lets you quickly compare performance, identify outliers, understand distributions across different segments.
Wow, okay.
And one more tip. It's generally good practice to ungroup your data after you're done summarizing, especially if you plan further operations down the pipe that shouldn't be constrained by those groups anymore.
Right. Release the grouping. That's incredibly powerful for generating those high-level insights. Okay, finally, sometimes our data structure itself isn't ideal for the specific analysis or visualization we have in mind. That's where pivot wider and pivot longer, reshaping for their appear. Different views come in. This really sounds like it lets us bend data to our will.
It absolutely does, and it's a surprisingly common requirement for many analytical tasks. Data often comes in, or is best worked with, in a long format, many rows, fewer columns. This fits the tidy data principles well and works great for many stats models.
Okay, long format, got it.
But sometimes, for reporting or specific plot types, you need a wide format where you have fewer rows but many more columns, often representing categories or time periods.
Can you give an example of that transformation?
Sure. Let's say we've summarized the mean arrival delay by carrier and month. The result would typically be in a long format, right? Like carrier month, mean or delay, UA110, UA215, AA8, A212.
Right, 1 row per carrier per month.
Exactly. Now, pivot wider could take that long data and transform it into a wide format, maybe making the months into columns. Carrier, month 1, month 2, UA1015, AA812.
I see. The month values became column headers.
Precisely. This wide format might be easier for a human to scan in a report, or maybe for a specific type of chart. And then, as you'd expect, pivot longer does the exact reverse. It takes wide data and makes it long again.
Okay, so you can switch back and forth.
You can. The ability to fluidly move between these formats is incredibly flexible and really a hallmark of the tidyverse's power to adapt data for pretty much any analytical need you might have.
That's really cool. Okay, shifting gears slightly. It's pretty rare, right, that all the information you need lives in one single perfect table. Often you have to bring data from different sources together, which leads us to connecting different worlds, merging data sets.
Oh, that's a profound truth in data work. And something a colleague once wryly observed sticks with me. There are two certainties in life: death and bad merges.
I believe it.
I still vividly remember a project where a seemingly straightforward left join unexpectedly quadrupled our data set size. Turned out there was an unhandled many-to-many relationship hiding in the joining key.
Oh, wow. Nightmare scenario.
Totally. Merging data sets is absolutely essential, but it's also precisely where these subtle complexities can lead to massive headaches if you're not really careful.
So thinking about our example, how does the flight's data set, our central hub, actually connect to these other tables within the Night Flights 13 package? What are the links?
Yeah, the Night Flights 13 package is designed nicely for this. The flight's dataset connects to the plane's dataset using a variable called tailnum.
The aircraft's unique ID.
Exactly. It links to the airline's table using the Carrier code, which lets you pull in the full airline name. It connects to the airport's table twice, actually once using the origin airport code and again using the Decius code, so you can get info about both airports involved in the flight.
Ah, clever.
And it even connects to the weather data table by combining multiple columns. Origin, year, month, day, and hour. That's a multi-key join right there, linking flight time and location to the weather conditions at that specific time and place.
Wow, okay. That shows how data can be interconnected.
Yeah.
So when we talk about actually joining these data sets in the Tidyverse, what are the different types of joins and why is choosing the right one so critical? You mentioned left join.
Right. This is where understanding your data relationships is absolutely paramount. The Tidyverse, mainly through Declare, offers several types of joins, and each one has really specific implications for what your final data set looks like.
Okay.
First, left join. This is probably the most common one you'll use. It keeps all the rows from your first or left data set and matches them with rows from the second data set based on the keys you specify.
Yeah, and if there's no match.
If there's no match in the right table for a row in the left table, it still keeps the left table's row, but it fills in the columns that would have come from the right table with NAs or missing values.
Okay, so you keep everything from the left table.
Exactly. Use this when you want to preserve all your main observations and just add supplementary information where it's available.
Makes sense. What else?
Then there's inner join. This one only keeps rows that have matching keys in both data sets. It's like finding the intersection. If a row in the left table doesn't have a match in the right or vice versa, that row gets dropped completely from the result.
So you only get complete matches.
Right. This is great when you only care about observations for which you have complete information from all the sources you're joining.
Okay.
Then there's right join. It's basically the opposite of left join. It keeps all rows from the right data set and matches from the left, filling with NAs if there's no left side match. Less common, maybe, but useful if your primary focus temporarily shifts to that right table.
Got it.
And finally, full join. This join keeps all rows from both data sets. If there's a match, it combines them. If a row in one table doesn't have a match in the other, it still includes that row, filling in the columns from the other table with NAs.
So it keeps everything from everywhere.
Pretty much. Use this when you want to ensure absolutely no data is lost from either table, even if it means ending up with a lot of NA values in the result.
Wow. So the choice here isn't just stylistic, is it? It fundamentally alters the scope, the size, and potentially the conclusions you can draw.
Absolutely. For example, flights % left join airlines by a carrier would add the full airline names to every flight record you have. But if you used an inner join instead, and maybe the airline's table was missing a small carrier that is in the flight's data, those flights would just disappear from your joined dataset.
Which could be a big problem if you didn't realize it.
Exactly. It could be an unintended consequence if you're trying to analyze all the flights. Understanding these distinctions is just crucial to avoid those bad merges we talked about and maintain the integrity of your data.
It's clear that these joining operations are incredibly powerful, but definitely demand careful thought to avoid unintended data loss or, like you said, duplication. Phew. We've covered a lot of ground today, really, from the whole philosophy of tidy data to the specific tidyverse verbs that let you actually manipulate it. So bringing it back, what does this all mean for you, the listener, the learner, navigating this world just awash in information?
Yeah, it's a lot, but I think this deep dive really reveals the tools that can truly empower your curiosity and your critical thinking when you encounter data. By mastering these data wrangling techniques and the tidyverse way of thinking, you're not just learning how to clean data, you're learning how to transform raw, sometimes messy information into a reliable, trustworthy analytical foundation.
Building trust in the data.
Exactly. It's about ensuring that your insights, whatever they are built on accuracy. And that enables you to ask more precise questions, gain richer understanding, and ultimately make more impactful decisions based on that data. It's really about moving from simply having data to truly understanding its structure, yes, but also its limitations and its potential.
What an incredible deep dive into making messy data magnificent. We've really seen how the tidyverse and its verbs empower you to select, rename, create new features, recode categories, precisely filter, logically arrange, powerfully summarize, strategically reshape, and intelligently merge data. Wow. all with incredible clarity and efficiency.
Indeed, it's a very coherent system. And maybe as you go about your day, you could consider how much unseen wrangling goes into basically every statistic you see, every report, every data visualization you encounter.
Right, like in a news article or a business presentation.
Or a research paper, anywhere. What questions might you ask now about the tidiness or the underlying preparation of the data behind those claims you're seeing?
That's a great closing thought.
Because truly understanding data, truly evaluating the claims made from it, it begins long before the first graph is drawn or the first conclusion is stated. It starts with understanding the wrangling. Thanks for joining us for this deep dive.